Welcome back to the course Data Science by RouteFabric, and today let's look at Bayesian Statistics. Bayesian Statistics mostly involves conditional probability, which is the probability of an event A given event B, and it is calculated by using Bayes' rule. The concept of conditional probability is widely used in medical testing, in which false positive and false negatives may occur. The Bayesian rule is that the conditional probability of event A conditional on the event B is given by probability of A given B is equal to probability of A and B divided by probability of B. Now let us look at Bayes' theorem. Bayes' theorem is an extension of conditional probability, stating that for two random quantities A and B, probability of A given B is that probability of B given A times probability of A divided by probability of B. Bayes' theorem relates the direct probability of a hypothesis conditional on a given body of data to the inverse probability of the data condition on the hypothesis. Now let us look at an example. You're planning a picnic today, but the morning is cloudy. 50% of all rainy days start off cloudy, but cloudy mornings are common. About 40% of days start cloudy, and this is usually a dry month. Only 3 out of 30 days tend to be rainy, or 10%. Now let us find the chance of raining given cloudy. So probability of rain given cloud is equal to probability of rain times probability of cloud given rain divided by probability of cloud. We're using the Bayesian theorem. Now the probability of rain in the question is given 10%. Probability of cloud given rain is equal to 50%. So there's a 50% chance when it rains it's cloudy. Now when we plug in all the values, the probability of rain when cloudy comes out to be 12.5%. So there's a 12.5% chance on raining given it's cloudy. Now let us look at frequentist inference. Frequentist inference is a type of statistical inference that draws conclusion from sample data by emphasizing the frequency or proportion of the data. Now let us look at what Bayesian inference is. Bayesian inference refers to statistical inference where uncertainty in inferences is quantified using probability. In Bayesian inference, the model parameter and hypothesis are not fixed, unlike in classic frequentist inference. We assign the probabilities to the parameters and the hypothesis. For example, it would not make sense in frequentist inference to directly assign a probability to an event that can only happen once, such as the result of the next flip of a fair coin. Now let us look at some statistical modeling. A statistical modeling is the process of applying statistical analysis to a dataset. A statistical model is a mathematical representation or mathematical model of observed data. Some examples of statistical modeling are logistic regression, naive Bayes, simple neural network. We will be seeing these models taken to a next level when we are talking about machine learning. Now let us look at the Bayesian decision theory. Bayesian decision theory refers to the decision theory which is informed by Bayesian probability, which we get by using the Bayesian theorem. It is a statistical system that tries to quantify the trade-off between various decisions, making use of probabilities and the cost function. We can pick the option whose expected value is the highest, for example, given the probability of rain versus the probability of cloud. The way that Markov chain works is that it creates each sample from scratch independently, and every time a new sample is made, a random change is made to the preceding sample. So there is high levels of randomness in the sampling. Now let us look at hidden Markov chain. A hidden Markov chain is a temporal probabilistic model for time series in which the state of the process is described by a single discrete random variable. The state transition over time is Markovian. The value of the state is unobservable. The unobservable is accompanied by another observable variable. Now what is Markovian? A stochastic process is Markovian if the following conditions are met. Given the present state, the future state of the process does not depend on the past state, then the process is said to be Markovian. Markov chain and Brownian motion are the common well-known Markovian processes. There are a couple of issues with hidden Markov chain. If the state space is too large, Markov chain struggles handling it in the discrete space. And if continuous variables are given to a hidden Markov chain during the discretization process, which is to converting continuous variables into discrete variables, the hidden Markov chain struggles a bit. Now let us look at a concept called particle filters. Particle filters is also known as the sequential Monte Carlos method, which is similar to the Markov chain Monte Carlos. It approximates the distribution using large number of samples, and these samples are sometimes called particles, hence the name particle filter. I hope this was informative. To learn more about data science, please visit RouteFabric.com. Thank you and have a nice day.